Okay, so we are going to talk about the second part of the neural network lecture. Today's topic is the backpropagation. That is the process to find out the partial derivative of your cost function with the function parameter. Cost function parameter. Okay. Linear regression. The process is to first we assume the initialize this function variable. In the previous example, we assumed the 1 and 0, right? 1 and 0, and then find out the cost function. No, not the cost function. It's the prediction, right? Prediction. And then compute the cost function. Okay. Once you find out the cost function, you're going to update the function parameter using gradient descent, right? So how to use the gradient descent? You're going to find out that this is a partial derivative of the cost function, right? So here's the gradient descent. We start from here, initial value, when theta is equal to theta 0, and then we compute the gradient vector, and then updated the theta. Here the theta 1 again is m and b, but in our neural network, this one goes to the weight parameter and bias, right? So it goes down in such a way that your cost function is the minimum. Okay? Our goal with the backpropagation is updated each weight and then in the network. Weight and bias. Okay? What is the weight and bias? That is the function parameter. So that they cause the actual output to be closer to the target output. Okay? Meaning that you're trying to minimize this cost function, right? Okay. Given a multivariate function f, x, and y, and two single-variate function x and t, meaning that x and y is the functions of the t, and then f is the functions of the x and y. So in this case, the partial derivative f with respect to the t can be represented as like this. Okay? And also here, f is a function of the g is a function of the t, partial derivative f t equal to okay. We're going to use this relationship to backpropagation process. Okay. Previous class we did the forward propagation. Forward propagations give you the value at each neuron, each node. So each neuron, here's the net, here's the out, right? So you compute this value in each neuron using this weight. Okay, I would say this one is a theta 0. Okay, we haven't updated this function parameter, right? E is the your cost function. The cost function is represented by the mean square error, right? like this. Okay, and then output is the output of each neuron is from the applying the activation function to the net value, right? So in the here's the output neuron, this one, and here's the net 1. This is the output 1. Okay. What about the net 1 output neuron? First output neuron, that is summation of the weighted summation of the connected neuron, right? So this one is connected to here and this one, right? H1, output H1, multiply the weight on this arrow, and then the W6, the weight on here, and then output H2, and plus a bias. Okay. These are the equations that we used in the previous feed-forward process, right? So how to compute the partial derivative of your cost function with respect to the W5? Okay. Before that, here, in this equation, the theta is not a single value, it's a multiple value, multiple the function parameter. So that's why I annotated like this in the previous example, right? This one is M, this one is a B. So basically this one is, if you updated W5, you're going to compute the partial derivative of the J with respect to the W5. So we're going to find out that this value. And here's the learning rate, right? Learning rate. Okay. So what is this value? Okay, E is the function of output O1, output O2, right? But here, what is this value? This one is your target output is the given value, right? This one. Okay. So this is not a variable. This one is a fixed value. So E is the cost function is a function of the output O1, output O2. That's why we like the equation like this, because E is the output O1 and okay, before that Ft is equal to F partial x over partial t plus partial f partial y partial t, right? Exactly same way here is a partial output O1 okay, let's erase this part, right? So E out O1 right? But this one, no, not this one. Okay, out O1 W5. This one is the same with out O1 out. This one is the same with out O1 net O1. Why? Output O1 is a function of the net O1. So we can expand these equations like this. Okay, partial E over the partial W5 can be represented summation of the T expanded these two equation. But here, net O2 is here. Here. Net O2 is connected with H1 and H2. The weight is W8 and W7, right? Meaning that net O2 is not a function of the W5. That's why this one is become a 0. So this only the first term is remain. Okay. Does it make sense? Okay. So let's compute the individual value. Okay, what about this value? So E goes to function is represented like this, minus x square E plus O2 minus y, let's say y or t, independent from the x. So this one is this become a 0, right? And then 2O1 minus x, partial derivative of this term is a minus 1. That's why, right? This one is this one. Okay? And partial derivative of O1 over the partial net O1 is what is this function? This one is your activation function. So go back to the partial derivative of your function. This one is just simply this one, right? So this value is the same with this one. Meaning that fx is the same with fx, f minus x. So you can write like this, okay? But here, O1 is the fixed value. What is the value of O1? Output O1. We compute this in forward propagation, right? We compute the value already in the forward propagation, even in the net O1, right? What about the partial net O1 over the partial W5? You can easily find out that is the output H1, right? Because the W6 and then B3 is not a function of the W5, so this one all the cancel out. We remain only the output H1. So finally, we find out the partial E over partial W5. That one is this value. Does it make sense? So your you can update this value. W5 is currently 0.5 minus alpha, I'll say 0.01 or certain value, multiply. Okay. This one is your new W5. Does it make sense? Let's move on to the how to compute the W1. W1 is the weight parameter is placed here. Okay. W1 E is the function of, right, like this, right? E is the cost function. So here, it's a function of output. So output O1 and output O2. So you can represent this one using the two term. But here we need this term as well, because you see this O1 and O2 is a function of H1 and H2, right? Because O1 is a weight summation of the H1 and H2. O2 is H1 and H2. That's why we cannot cancel out the one of a term. Okay. And here, okay, and this value, this one, this value goes to here. And we're going to find out this value. What is the partial net O1 over partial W1? Partial O1, here, partial O1 is a function of output H1 and output H2, right? Basically, this one is partial net O1, partial W1 is the partial net O1, partial out H1, partial out H1, W1 plus net O1 out H2 out H2, right? But we can expand this one using this two term. Okay. What is this value? Is partial net H2 over W1, partial W1. W1 is not connected to the H2, right? H1 is connected to only the H1, so this is 0. You can only compute this value. So here, net O1 over the output H1, that one is this equation. So the value is W5, right? This one is W5. And this value is, we know that this one is a partial derivative of, derivative of your activation function. That one is this one. What about this one? Net H1. Net H1 is, where is net H1? Here, right? So over the W1 is the I1, right? Right? You can compute the net O2 over the W1 in the similar way. Okay? So again, all this value here, all this value is the from your input and the value in the neuron, or the weight that we used, that we compute in the forward process. So this value become this one. This one is the here. This one. Okay, this one is the here, right? Okay. Here, and this value, this one, okay. We did this partial derivative of your function of your parameter for the case of W5 and W1, right? Once we find out that this value, we can get the new W1. Okay? To make clear, here we find out the W5 and W1 using the W5 and W1, and we finding out that this one from the back propagation, and we update it. That's the process. Back propagation is that process. Okay? So we can finding out all these other parameters W2, W4, and B1 in the similar way. Then you're done. Backpropagation is done. What is the backpropagation again? So you've computed this partial derivative and updated your parameter. Okay. Okay, if you see this equation, it looks very complex. There are many terms are involved in this computation, right? But let's compare it's a full equation. Okay. We realize that some of the term is keep reused, right? This blue is here. So meaning that, so let's say here's the input layer, so hidden layer and output layer. So if you compute this partial E or somewhere here, maybe parameter, we reuse this some value already computed in the top layer for computing this partial derivative value in the lower layer. Here's the top. Okay. So we can compute this partial derivative of each parameter in more systemic way. For instance, this one is a forward propagation. So we can define this input and output of each wave parameter as a network, as a matrix, not network. For instance, here WIH means input and first the hidden layer. We make an array 2 by 2 because 2 node and then two input and 2 output. Size of the input, the number of input and number of output nodes are increased. The size of this matrix also increased. This one is a bias term. And also we can make another matrix of the weight parameter between the hidden layer and output layer. And we can make the net and out. You remember the net and out for each neuron. So this one is H net in the hidden layer and H out for hidden layer. These are for the output layer. H net, H output value can be computed using this matrix computation. All these other parameter, other value in the neuron in the network can be computed using this matrix operation. Okay? Similarly, we can do the backpropagation using the matrix multiplication. So here, so if you see that to compute this, for instance, here, where we use the partial derivative of each neuron and then the net and weight parameters and net and another neuron, we can use all this partial derivative value in order to compute this partial derivative value for the lower layer. That's why we defined this matrix for each node and each layer. For instance, here ON is output and net. Output net in the output node. Then E and O is a cost function and output is here, right? So net and W5 is here, W5 and then net. net and W5. HON is output and net in the hidden node, at the node in the hidden layer. And W is net and W. Okay. EO is the input node. So net input. So here's I1 and then here's the net value. Okay. Okay, let's take a look at the, but basically we used all this 6 matrix, no, all the 7 matrix for computing all the partial derivative value. Okay. So how to compute this value in this each of the matrix? We can compute this value using the value in the node that we computed in the forward propagation. For instance, net, so partial derivative output and partial derivative net is so when we use a sigmoid, this one is a net O multiply the sigmoid function of the minus net O1, right? We already computed this value in the forward propagation, right? But in this case, the output H1 is also computed in the forward propagation. Output O2 is the predicted value, right? Similarly, all this matrix value computed, the value that we obtained in the previous forward propagation, or so current weight value, and this one is the input value. So for instance, here's the partial derivative of the cosine function with respect to the W5 can be computed simply in a matrix, or in this case element-wise multiplication of the 3 matrix. If you do this process, you can get all this value. Similarly, you can find out the W1 to 4 using this operation. So no matter we're increasing the number of neurons, the number of hidden layer, you can compute the, for instance, net output and that partial net over net output and partial net over the connected weight parameter. For instance, if there's a node connected to the another neuron, connected to other neuron, so here's out, right? Here's the net, here's out, here's the net. So maybe net 2, 1, 2, 0. So each node we are computing the net 2, out 1, out 1, out net 1, out net 1, out 0. So basically we're computing this 3 value in each node, and then forming this matrix. Then finally we'll get this so derivative value using this matrix operation. Okay, here is the summary of the neural network process. First step is to design the neural network. Depending on your applications, for instance, a regression or classification, you need to update the activation function, loss function, and then activation function on the final neuron, output neuron. And also depending your complexity of your model, you're going to design the number of hidden layers and number of the neuron in each hidden layer. And also you can design the number of nodes in the input layer depending on your dimension of your input data. Okay? And also you can think of some default learning rate and some kind of the other technique to improve this modeling gradient descent performance. For instance, learning rate scheduling or adding the momentum term. That's the first step. The second step is that you initialize the weight and bias on your neural network. Here, I manually assign some specific value to the weight and then bias. But normally, we are randomly initialize this value. In the MATLAB example, the tutorial code, I assign the random Gaussian noise, random Gaussian value to this wave value. Okay. Then we put the input and output value. These are the given input and output value. And next step, we do the forward propagation. Again, the purpose of the forward propagation is to compute your cost function based on the prediction here. Okay? Using the current weight and bias value and then given input value, you're going to compute the value of each neuron. In here, net value, and here's the output value activation function, right? This blue value indicate the value on each neuron. Okay, and then step 4 is a backpropagation. Backpropagation is to find out the derivative of your cost function with respect to your model parameter. Here is the weight and bias. Okay. In the previous slide, we saw that to compute this value, we need to have the value of each neuron that we computed in the forward propagation step. Using those values, we are going to find out 1, 2, here is 8, and bias as well. Okay. And next, once we find out this gradient vector, then we updated our parameter. Okay, this is some kind of general process of the neural network. But in here, depending on the gradient descent process, so this step is a little bit different. For instance, stochastic gradient descent, you can update the weight parameter for using each of your data. So once we finish the step 1, we keep repeating S2 to S5 n times. N is the number of data. Okay. But batch gradient descent is different. Batch gradient descent, your cost function is computed from all your data. So in this case, so S2, S3, n times, and S4 and S5, only one time. Okay, that's this one. Okay, mean batch gradient descent is somewhere between the batch and the stochastic gradient descent. You can only the b times because we are using the b number of data, and then update a parameter, and then go back and then observing another data set. Okay. So that's the process. So in the forward propagation, you remember that you can draw the mask here. Yeah, that's the neural network function. You put the input data, it gives you the predicted output, and using the target output value, you're going to see the difference between them. That is the cost of function. Once we find out that to compute this predicted outcome, you're going to compute all the value in the neuron. So backpropagation is to compute this partial derivative of your cost of function using the value on the neuron, weight, and input data. Okay, that's it. That's the end of the today's lecture. But one missing part is I use the term of epoch. Epoch means so you training your model using all your data. So like one iteration, but we normally say that one iteration in the stochastic distance is using the one single data or the one forward propagation. We refer to iteration of that process, but one epoch means we observed one whole entire data set. So here, if you update the parameter, that is a one epoch, because in the batch gradient descent process, you only the backpropagation only the one time for entire data set. Okay, so that is the one epoch. Okay, in the stochastic gradient descent, I also use the epoch. So when updated your parameters and time using the n different data set. Okay, that's it. So I uploaded the tutorial neural network code as well as the sample. You utilize those sample code and the sample demo to solve your task 8. Great. See you.